Welcome to this video on the behavior of gradients at maximum and minimum points. Understanding how gradients behave at these critical points is essential for solving optimization problems in calculus and many real-world applications. Before we dive into the behavior of gradients at extrema, let's first understand what a gradient is. The gradient of a scalar function is a vector that points in the direction of the greatest rate of increase of the function. Its magnitude represents how quickly the function is increasing in that direction. We denote the gradient of a function f with this nabla symbol, which is read as del f. For a function of two variables, the gradient is composed of the partial derivatives with respect to each variable. Let's visualize this with a simple function. Here's a function z equals negative x squared minus y squared plus 4, which represents a paraboloid opening downward. The arrows represent the gradient vectors at different points on the xy plane. Notice how they all point toward the center, which is the highest point of our function. As we get closer to the maximum point at the origin, you can see that the gradient vectors get smaller. Exactly at the maximum, the gradient becomes the zero vector. This is a crucial observation. At extrema, the gradient vanishes. Let's formalize this observation. At a local maximum or local minimum of a differentiable function, the gradient is the zero vector. Mathematically, this means nabla f equals 0. Why is this the case? Let's think intuitively. If you're at the top of a hill, which is a local maximum, moving in any direction will cause you to go downhill. At that exact peak, you're not going up or down in any direction. Hence, the rate of change, the gradient, is 0. Similarly, if you're at the bottom of a valley, which is a local minimum, moving in any direction will cause you to go uphill. At that exact lowest point, you're also not going up or down in any direction, so the gradient is again 0. The points where the gradient is 0 are called critical points or stationary points. These are candidates for local maxima, local minima, or saddle points. Speaking of saddle points, these are interesting cases where the gradient is 0, but the point is neither a maximum nor a minimum. A saddle point is like the center of a saddle shape, where in one direction it's a maximum, and in the perpendicular direction, it's a minimum. For example, consider the function z equals x squared minus y squared. At the origin, the gradient is 0, but it's a maximum along the y-axis and a minimum along the x-axis, a classic saddle point. So, how do we determine whether a critical point is a maximum, minimum, or saddle point? We use the second derivative test. For functions of two variables, we calculate the Hessian matrix, which contains all the second partial derivatives of the function. The Hessian matrix looks like this, where f underscore xx means the second partial derivative with respect to x twice, and f underscore xy means the partial derivative with respect to x, and then with respect to y. We then calculate the determinant of this matrix, which we'll call D. If D is positive and f underscore xx is positive, then the critical point is a local minimum. If D is positive and f underscore xx is negative, then it's a local maximum. If D is negative, it's a saddle point. And if D is 0, the test is inconclusive. Let's see how this works with our examples. For the paraboloid z equals negative x squared minus y squared plus 4, the Hessian at the origin has f underscore xx equals negative 2, f underscore y equals negative 2, and f underscore xy equals 0. The determinant is 4, which is positive, and f underscore xx is negative, so this confirms it's a local maximum. For the saddle function z equals x squared minus y squared, the Hessian at the origin has f underscore xx equals 2, f underscore y equals negative 2, and f underscore xy equals 0. The determinant is negative 4, confirming it's a saddle point. Before we conclude, there are a few important considerations to keep in mind. First, the gradient only tells you about local extrema in the interior of the domain. You also need to check the boundary of the domain for potential maxima or minima. Second, finding local extrema doesn't guarantee you've found the global maximum or minimum. You need to compare the values at all critical points and boundary points. Third, if the function is not differentiable at a point, the gradient is not defined there, but these points could still be extrema. In conclusion, the gradient being 0 is a necessary but not sufficient condition for a local extremum. The gradient's behavior provides crucial insights for optimization problems, helping us identify and classify critical points as maxima, minima, or saddle points. Understanding these concepts is essential for solving optimization problems in calculus, physics, economics, machine learning, and many other fields. Thanks for watching.